"2025 Nobel Prize in Physics, explained in 5 minutes. Understanding the 2025 Nobel Prize in Physics in clear and easy language. By Physics Explained. The 2025 Nobel Prize in Physics was awarded to John Clark, Michel H. Deverett, and John M. Martinis for the discovery of macroscopic quantum mechanical tunneling and the observation of energy quantization in an electric circuit. To understand why the prize was awarded to John Clark, Michel H. Deverett, and John M. Martinis, you need to understand 4 key ideas. 1. Quantum tunneling. 2. What makes this discovery special? 3. Energy quantization in Josephson junctions. 4. Quantum tunneling in Josephson junctions. Quantum tunneling. In classical physics, a particle cannot cross an energy barrier if it doesn't have enough energy. An electron is like a soccer ball rolling toward a brick wall. If the ball doesn't have enough energy, it will hit the wall and bounce back. It can never cross the wall unless it has enough energy to break it. Thanks for reading. Subscribe for free to receive new posts and support my work. Classical rule. No energy means no crossing. That's how classical physics behaves. In quantum mechanics, particles behave like waves. Because of this wave nature, a particle can tunnel through a barrier it classically shouldn't cross. This is a purely quantum effect, with no classical explanation. Why it matters? Quantum tunneling is usually microscopic, electrons, atoms, etc. What these scientists discovered happens on a much larger scale. If you're reading this, you're already my kind of audience. I write here on Substack and post companion videos on YouTube. Subscribing is the easiest way to support the work. What makes their discovery special? This Nobel Prize recognizes the first clear demonstration that a macroscopic object, something involving trillions of electrons acting together, can behave according to quantum mechanics. They showed that a whole electric circuit behaves as a single quantum object. The circuit can tunnel. The circuit's energy can only take quantized values. This means quantum mechanics applies not just to particles, but to large engineered systems, which is foundational for quantum computing. Let's explain how a whole circuit can act like a quantum object. Energy quantization in Josephson junctions. A Josephson junction is the core building block of many superconducting circuits. It consists of 2 superconductors, separated by a very thin insulating barrier. Electrons in a superconductor don't act normally. They form Cooper pairs. Normal metal. Electrons move individually, white dots, and constantly scatter, which creates resistance. Superconductor, top right. Electrons form Cooper pairs. These pairs act very differently from single electrons. Superconductor, bottom. All Cooper pairs collapse into one coherent quantum state, the long white line. This means the entire superconductor shares a single quantum state. This macroscopic quantum state is described by a single phase phi. This phase becomes the key variable in Josephson junctions. In a Josephson junction, what matters is the phase difference between the 2 superconductors delta. The energy of the junction U, which depends on this phase difference, becomes quantized. This phase difference is a macroscopic quantity that behaves quantum mechanically. It can be in a superposition. The phase difference across the Josephson junction is a quantum variable. Because the junction has quantized energy levels, the phase does not need to stay in only one level. It can be in a superposition of several levels at the same time. Quantum tunneling in a Josephson junction. The phase difference in the junction sits in a potential well, like a ball resting in a valley. Classically, the ball is stuck because it does not have enough energy to climb over the hill. Quantum mechanically, the phase can tunnel through the hill as shown above and appear in the next valley, even if it does not have enough energy to go over the top. This tunneling event makes the junction escape from the zero-voltage state and produces a measurable signal. This is called macroscopic quantum tunneling because it involves the collective motion of many electrons acting as one quantum object. This forms the basis of quantum qubits because the junction can occupy a superposition of 2 energy states, which we call the qubit. This is what they won the Nobel Prize for. They showed that a macroscopic variable, the small phase difference delta across a junction, can behave quantum mechanically. This discovery is now the foundation of superconducting qubits used in today's quantum computers, including those built by Google and IBM. If you're reading this, you're already my kind of audience. I write here on Substack and post companion videos on YouTube. Subscribing is the easiest way to support the work.